Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, ultra-high cosmic rays, Integral's legacy, and Andromeda's hidden companions. The origin of ultra-high energy cosmic rays unveiled. Ultra-high energy cosmic rays, UHICRs, are the most energetic particles known in the universe, possessing energies millions of times greater than what can be achieved by any human-made particle accelerator. Despite being known for over 60 years, their origin has remained an unresolved mystery, with no comprehensive explanation that aligns with all observational data. However, a new theory introduced by physicist Glenys Farrar from New York University offers a viable and testable explanation for the formation of these extreme cosmic particles, potentially solving one of the biggest enigmas in astrophysics. This new insight suggests that UHICRs originate from the powerful and chaotic magnetic outflows that occurred during the merger of two neutron stars, just before the formation of a black hole. Such events, among the most cataclysmic in the universe, not only generate UHICRs but also produce strong gravitational waves, some of which have already been detected by observatories like LIGO and Virgo. These neutron star mergers play a crucial role in the synthesis of heavy and exotic elements such as gold, platinum, uranium, iodine, and xenon, reinforcing their significance in both astrophysics and cosmic chemistry. The proposal, published in the journal Physical Review Letters, introduces a mechanism in which UHICRs are accelerated within the highly turbulent magnetic fields ejected by the merging neutron stars. These extreme environments, characterized by immense gravitational forces and violent magnetic turbulence, provide the necessary conditions to propel charged particles to ultra-high energies. This process differs from other previously hypothesized acceleration mechanisms, such as those involving supermassive black holes or active galactic nuclei, by directly linking the production of UHICRs to neutron star mergers. One of the key aspects of this theory is that it explains two of the most puzzling characteristics of UHICRs. The first is the precise correlation between a UHICR's energy and its electric charge, a feature that has lacked a clear theoretical foundation until now. The second is the sheer energy of the most extreme events recorded, which surpass what traditional astrophysical accelerators were expected to produce. Farrar's model accounts for both by demonstrating how these particles originate in rare R-process elements, such as xenon and tellurium, that are ejected during the merger process and subsequently accelerated to astonishing speeds. Beyond offering a theoretical framework, this proposal has practical implications for future research. If correct, it suggests that the highest energy UHICRs should exhibit signatures of these heavy elements, prompting a targeted search in observational data to confirm their presence. Furthermore, it establishes a fundamental link between the production of UHICRs and the detection of gravitational waves. Whenever UHICRs are generated in a neutron star merger, extremely high-energy neutrinos should also be produced in subsequent particle collisions, forming a characteristic pattern of detectable signals. This new understanding represents a major breakthrough in high-energy astrophysics, providing not only a compelling answer to the long-standing mystery of UHICR origins but also a predictive framework that can be tested with future observations. If confirmed, it will enhance our ability to study and interpret some of the most violent and energetic processes in the cosmos, deepening our knowledge of both cosmic particle acceleration and the extreme environments that shape the universe. Integral's legacy, 2 decades of gamma-ray discoveries. This week we had the conclusion of the European Space Agency's Integral mission, a gamma-ray telescope that has spent 22 years reshaping our understanding of the most extreme and dynamic events in the universe. Since its launch on October 17, 2002, from the Baikonur Cosmodrome in Kazakhstan, Integral has played a fundamental role in unveiling the nature of cosmic explosions such as gamma-ray bursts and in identifying the sources of gravitational wave events. Throughout its operational lifetime, it provided crucial insights into the physics of thermonuclear blasts and neutron stars, revealed how these cataclysmic events generate powerful jets, and captured a rare giant flare from an extragalactic magnetar. Integral's contributions have been particularly significant in the study of gamma-ray bursts, which are among the most energetic and brief flashes of radiation in the universe. These bursts occur roughly once per day somewhere in the sky, outshining all other gamma-ray sources combined for a short period. Today, it is well established that longer bursts, lasting several seconds, are caused by the core collapse of massive stars going supernova, while shorter ones originate from collisions between neutron stars or black holes. Integral played a key role in refining these classifications and in confirming that some of these events are directly linked to gravitational wave detections. One of the most remarkable aspects of Integral's legacy is its ability to make unexpected discoveries, surpassing the initial goals of its mission. At the time of its launch, direct detection of gravitational waves was still an open question in astrophysics, and it would take another 13 years before the first confirmed observation by the LIGO detectors in 2015. Yet, Integral proved invaluable in identifying electromagnetic counterparts to these spacetime ripples, helping scientists trace their origins to cosmic mergers. The telescope was also instrumental in detecting ultra-high energy neutrinos, elusive particles that can travel across the universe, providing a new way to study the most extreme environments in space. Even in its final years, Integral continued to deliver groundbreaking results. One of its most striking observations was the detection of the most powerful gamma-ray flash ever recorded, a burst so intense that it had a measurable impact on Earth's ozone layer. This event, originating in a galaxy nearly 2 billion light-years away, demonstrated the astonishing reach of cosmic explosions, revealing how distant astrophysical phenomena can still influence our planet. More recently, Integral captured an extremely rare magnetar outburst that, in just 0.1 seconds, released as much energy as the Sun produces in 500,000 years. Another major finding was the discovery that thermonuclear explosions on neutron stars can drive powerful jets, offering new insights into the mechanisms shaping these extreme objects. At the time of its launch, Integral was the most sophisticated gamma-ray observatory ever built, and it was the first to observe celestial objects simultaneously in gamma rays, X-rays, and visible light. Its success was made possible by three key features of its instrumentation: a large field of view covering about 900 square degrees of the sky, the ability to capture both detailed images and high-energy spectra at the same time, and the support of X-ray and optical cameras to help pinpoint gamma-ray sources with precision. These capabilities allowed it to revolutionize the study of high-energy astrophysics and to provide data that will continue to shape the field for years to come. After completing 2,886 orbits and more than 2 decades of observations, Integral's instruments ceased their scientific operations. However, its legacy will persist through the vast archive of data it has collected, which will remain an essential resource for future research. ESA has ensured that this treasure trove of information will continue to support new discoveries and inspire upcoming generations of astronomers and engineers. While the spacecraft will no longer be conducting observations, it will continue orbiting Earth for another 4 years, with ESA engineers monitoring its trajectory until its planned re-entry into the atmosphere in early 2029. Thanks to a carefully planned thruster burn executed in 2015, Integral's re-entry will comply with ESA's commitment to reducing space debris, marking the end of its journey in a responsible and controlled manner. Integral's mission may have officially ended, but its impact on astrophysics will endure. By revealing the hidden universe in gamma rays, it has expanded our understanding of the most violent processes in space, from supernovae to black holes, neutron stars, and magnetars. The data it has provided will continue to fuel new discoveries, ensuring that its contributions to science remain invaluable long after its final orbit. Andromeda's hidden companions. The Andromeda Galaxy, situated 2.5 million light-years away, presents itself to the unaided eye as a subtle, elongated smear in the sky with an angular size similar to that of the full moon. Yet, beyond this faint visage lies a complex and bustling system composed of nearly 36 diminutive satellite galaxies that orbit Andromeda much like a swarm around a central hive. This intricate arrangement of dwarf galaxies forms a lively galactic ecosystem that has recently been the focus of extensive investigation by the Hubble Space Telescope through an ambitious Treasury program. Over the course of more than 1,000 Hubble orbits, astronomers have been able to construct a detailed three-dimensional map of these satellites and analyze the history of their star formation, extending over nearly 14 billion years of cosmic evolution. The results of this extensive survey, recently detailed in a peer-reviewed scientific journal, reveal a stark contrast between the satellite systems of Andromeda and our own Milky Way. While the Milky Way exhibits a relatively sedate environment, Andromeda's more dynamic past is evident in the diversity and abundance of its orbiting dwarf galaxies. It appears that a major collision with another large galaxy a few billion years ago, combined with Andromeda's significantly larger mass, has led to the creation of a more varied and populous collection of satellites. This difference provides valuable insights into the distinct evolutionary paths taken by the two neighboring giant galaxies. Observing the full complement of satellite galaxies around our own Milky Way proves challenging because we are embedded within it, and such detailed studies are even more difficult for other distant galaxies. Andromeda, however, is close enough to allow astronomers to examine its faint companions in considerable detail, offering a unique perspective on how a massive galaxy can influence the growth and star-forming activities of its smaller neighbors. The duration of star formation within these dwarf galaxies appears to depend strongly on both their intrinsic mass and their proximity to Andromeda, suggesting that the gravitational and environmental effects of a dominant galaxy play a critical role in shaping the evolution of its satellites. Further examination of the Andromeda system reveals a marked asymmetry and disruption in the distribution of its satellites, hinting at a recent, significant event that altered their orbits and configurations. Notably, about half of these dwarf galaxies seem to share a common orbital plane, all moving in the same direction, a configuration that challenges current models and remains a subject of active investigation. Among the satellite galaxies, the brightest is a compact elliptical object known as Messier 32, which is thought to be the stripped remnant of a once larger galaxy that collided with Andromeda. Despite containing primarily older stars, Messier 32 also exhibits evidence of a burst of star formation that occurred a few billion years ago. Moreover, there exists a distinct subset of Andromeda's dwarf galaxies that, contrary to expectations from theoretical models, managed to sustain star formation over an extended period, albeit at a low rate, well beyond their initial epoch of stellar birth. These observations not only underscore the diversity within the Andromeda satellite system but also highlight the challenges in understanding the full scope of galactic evolution. The dynamic interplay between gravitational forces, the availability of gas, and the inherent properties of the dwarf galaxies themselves results in a complex history that is only beginning to be unraveled. Future observations, whether from continued Hubble campaigns or from next-generation instruments like the James Webb Space Telescope, promise to extend these studies by measuring the motions of the dwarf galaxies. Such data will eventually enable astronomers to reconstruct the entire dynamical history of the Andromeda system, tracing back the paths of its satellites over billions of years and offering a clearer picture of how large galaxies and their companions co-evolve through cosmic time.